If you're a developer, you've definitely had that moment. You're thinking about a chunk of code, and your AI assistant just suggests the exact thing you were about to write. It honestly feels like magic. But, behind that magic is one of the most fascinating engineering puzzles in modern AI. So let's pull back the curtain and see how these things are actually built.
You just type a simple comment, a little hint of your intention, and bam, a perfectly good function just appears. This is the promise of coding AIs like GitHub Copilot. They seem to understand not just programming languages, but what you're actually trying to do. We've gone way beyond simple autocomplete here. This feels like a real collaborator.
So is it magic? Well, no, not quite. It's really the result of solving a series of incredibly complex puzzles. And in this explainer, that's exactly what we're going to do. We're going to look at how engineers manage to tame the absolute chaos of internet code, how they teach an AI to think like a developer, and this is the big one, how they make sure the code it writes actually works. All right, puzzle number one starts with the raw material, the training data. I mean, to teach an AI to code, you need a staggering amount of examples. But just scraping all the code off the internet, that creates its own set of absolutely colossal problems. Just think about it for a second. Public code repos are just full of forks, endless copies of the same thing, abandoned projects, and even malicious code. If you just naively fed all of that into a model, you'd be training it to be repetitive, insecure, and full of really, really bad habits. So the very first job is to clean up this massive digital junkyard. So the question is, how do you get from that chaotic mess on the left to the pristine, high-quality data set you see on the right? This right here is the first monumental engineering challenge. It's all about transforming raw noise into a clean signal that the AI can actually learn from. And this is how it's done. It's a super rigorous multi-stage pipeline. First up, they filter for code with permissive licenses. That's just basic respect for intellectual property. Then comes a massive deduplication process. This uses some really clever algorithms to remove not just exact copies, but near copies too. After that, they scan everything for potential malware, and finally, they validate that the code is syntactically correct and well-formed. Only the best of the best actually makes the cut. Okay, so now we have clean data. Awesome, but that's really only half the battle. See, that data teaches a model to predict what comes next. But we developers don't just write code in a straight line, right? We edit, we insert, we refactor all over the place. So how do you teach an AI to think like that? Well, that brings us to our second puzzle, thinking inside the blanks. The key innovation here is a technique called fill-in-the-middle, or FIM for short. Instead of just trying to predict the next word, the model is trained to predict a whole missing chunk of code. You give it a prefix and a suffix, the before and after, and its job is to generate the part that connects them. This one simple shift is what gives these AIs their incredible ability to work inside your existing code. It's a game changer. But, not all FIM is created equal. The early versions just split the code randomly, which is totally unnatural. The real breakthrough was AST-Aware FIM. It uses the code's underlying structure, its abstract syntax tree, which is kind of like a grammatical map of the code's logic, to hide entire logical blocks, like a whole function or a loop. This trains the model on examples that actually mimic how a human developer thinks and edits, which makes it so much more powerful. Okay, so our model can now generate syntactically correct code in a very human-like way. That's huge. But how do you teach it the difference between code that just looks right and code that actually runs correctly? This is the judgment puzzle. And believe me, it is a big one. And this really is the crucial question, isn't it? Unlike natural language, where correct can be pretty subjective, code has a very clear objective standard. Does it pass the tests or not? The challenge is figuring out how to use that objective truth to guide the model's learning process, automatically and at an absolutely enormous scale. The solution is to move beyond subjective human feedback and just use the code's own functional correctness as the reward signal. In other words, if the code it generates passes a bunch of unit tests, it gets a thumbs up, a positive reward. If it fails, it gets a thumbs down. This gives you a clear, scalable way to get the AI to produce code that actually works. Now, this gets even cooler with more advanced training methods. They've basically created a kind of adversarial game between two different AIs. You've got one AI, the coder, that's trying to write correct code. Then you've got another AI, the tester, whose whole job is to write unit tests that break the coder's code. So the coder gets better by learning to pass the tests, and the tester gets better by finding even more subtle bugs. They just keep pushing each other to get better and better. So let's recap. We have clean data, a really smart training method, and a way to verify correctness. The final puzzle piece is putting it all together right inside your editor, making it aware of your entire project, not just the one file you happen to be looking at. And that's the key right there. A super powerful model is pretty much useless if it doesn't have the right information at the right time. The very best AI assistants are absolute masters of context. It's a field that people are now calling context engineering. So where does it find all this context? Well, pretty much everywhere. It looks at the code you're literally writing right now, but it's also looking at your other open tabs. It uses something called vector embeddings, which is a fancy way of turning code into numbers, so similar concepts are closer together, to find related code from all over your repository. It pulls in definitions from libraries you've imported and even considers files you've recently worked on. It's building this whole picture of what you're trying to achieve. And all of this happens in a lightning-fast pipeline. As you type, your IDE is sending symbols to a context retriever, which acts like a little search engine for your codebase. Then, a prompt assembler skillfully packages all the best, most relevant info into a compact prompt that the model can handle, before sending it off to the LLM to generate that magical suggestion. And that really brings us to the big question. When you solve all of these incredible engineering puzzles, you don't just get a better tool, you get a partner. As these systems move from simple autocompletes to something more like autonomous agents, the role of the developer starts to shift from being a writer of code to an architect of systems, a high-level guide for an incredibly powerful collaborator. So, what do you think that future looks like?